Okay, so as the last second talk, I will talk about water purification during riverbank filtration, and I'll focus on antibiotic removal from reclaimed water. Okay, so here we go. As we all know, riverbank filtration is a widely used technology all over the world, kind of to recharge the aquifer. And basically, the process is describe the raw surface water infiltrate the riverbank and partly riverbed to the depleting aquifer. But actually, nowadays, with the cities developed and with the society move on, I think not only the amount of the groundwater and also the clean surface water is reducing, but on the other hand, the amount of the reclaimed water is increasing. So another alternative way is to use the reclaimed water in the riverbank filtration to recharge the aquifer. So the advantage also is not only restore the dried nature river, but also replenish the decreasing on groundwater. Another advantage of this is reclaimed water has a constant and reliable. Thank you. And has a constant and I'm too short for this, sorry. And has a constant and reliable supply, but there's also pose another risk behind this because the water quality of the reclaimed water is lower than the groundwater. So maybe we'll pose some potential contamination about this. So this is also our study area. So the North China Plan. Before I goes to detail about the North China Plan, I would like to show you where it locates. So this is the map of China, and this is North China Plan, located in the north part of China. And we are not going to focus on the whole plan, but also the Beijing Plan, because 17% of the raw water in the plan is from the reclaimed water. So what will happen about the water quality in the groundwater system and in the raw water system is showing here. So we go. This one shows the water quality of the surface water and the water quality of the shallow aquifer. And now we go to much more detail. This part is the Beijing Plan, and this different line is the river water. So the different color represents the quality, the water quality of the river water. So also the different color represent the different quality, and the explanation here. So it's the same color for the shallow aquifer water. And when we take specific river water here, we can see here in the shallow aquifer system, the groundwater just below the river is hotspot for water pollution. But if it goes a bit far away from the river water, it's like the water quality is increasing. So maybe the correlation, it suggests that the reclaimed water, when it recharges the aquifer, can cause some water pollution and may bring different kind of pollutants to the aquifer system. And among all of the pollutants, I'm going to talk about antibiotics. And why I talk about antibiotics? Because it's important, is a medicine compound. And actually, we use a lot, and 17% of the chemical I take in is discharged to the natural environment and with unchanged function. And they are quite persistent and cannot be completely removed from the wastewater plant. And even low concentration in the natural river can increase a lot the antibiotic resistant genes, so create super bacteria which will threaten our health, not only human beings, but generally all the living beings, I think. So the aim of my study is going to evaluate the removal process of antibiotics during the riverbank filtration. In my study, I focus on the lab scale study. So also going to assess the potential influence factors on the removal performance, like a substrate, and also the different sediment type based on two hypotheses. The first one is extra substrate like organic carbon and inorganic nitrogen can favor the removal performance. And another hypothesis is quite simple. Different sediment type can have different removal performance. And maybe sediment with a higher microbial abundance or diversity is more diverse, so it will help remove the micropollutants. Okay, so before I'm going to introduce a lab experiment, I also want to know, okay, so what happened in the field site? To answer this question, we have different sampling campaign for the river water and for the groundwater. So the river water sampling may detect along this river, as I introduced before. These 3 bullet points represent 3 field sites that with some monitoring wells at the riverbank. So we'll also take groundwater samples at this point. And here is the example of the field site. So this is the river, and the different points represent different monitoring well at the bank. So, and they have different riverbank distance. And this cross-section of the monitoring site just shows the monitoring well has different depths in the unconfined aquifer. So we take the samples from the river water and the groundwater, and we measure the pollutants in the lab. So generally, different antibiotics could be measured, including sulfonamides, tetracyclines, and quinolones. And generally, the antibiotic concentration in the river water is higher than the groundwater. And also this tendency can be seen here. So this is the sulfamycin, a kind of antibiotics, the measured concentration at the different monitoring well at the bank. So they have the different well has different riverbank distance and have different depths in the confined aquifer, but all of this concentration kind of show a lower compared to the concentration in the river. So when I found this decreasing pattern, I think must be something happened. And check some references and some literature. It can be dilution, it can be absorption, and it can be degradation. So I want to focus degradation. I just want to emphasize. Okay. But I'm not sure if all of you have a degradation background, so just briefly update a bit. So based on the references, there are 2 different pathways, like most commonly talked about in the papers, is like called metabolism and co-metabolism. So for the metabolism is the trace organic carbon, like in my case is antibiotics, can be utilized by the bacteria directly. So the antibiotics, the trace organic carbon used as carbon source or provide energy source for the bacteria to grow. And it can be converted to the small molecule metabolites. It can continue to be converted, and also in one case it can be converted to CO2. So if the end product of the metabolism is CO2, it's also called mineralization process. And compared to metabolism and the co-metabolism is the trace organic carbon, the concentration is too low or is a bit toxic for the bacteria, so it cannot be directly utilized by the bacteria. So the bacteria use some extra growth substrate like dissolved organic carbon or ammonia to produce energy, and by some chance they also decrease or remove organic carbon and then convert to metabolites and so on. So it's just to compare to these 2 different pathways, the growth substrate is mandatory, is necessary in the co-metabolism. And if you want to find some more detail, there's a nice paper published several years ago, is talking about these 2 different pathways. Okay, so here is the lab experiment. Basically, I have the batch experiment. One is called river batch, another one is mineralization batch. So for the removal batch is the antibiotics I use is sulfonamide mixture of sulfamycin, sulfadiazine, sulfamethoxazole, and the 10 microgram gram per liter is a bit relatively higher than the concentration I found in the river, but it's also quite nature environmental related concentration. So first, I just test the oxic condition and with river sediment, and another called mineralization batch. So the difference here is not use the normal antibiotics, but use carbon-14 labeled antibiotics to study the mineralization potential. And also different river sediments which used. So also I sampled the riverbank and riverbank sediment along this river. So mainly is still at these 3 field site points, 3 field site I introduced a bit earlier. So in each site, riverbank sediment and also riverbed sediment was collected. So this is also because I want to test the different effects of the sediment type, how they will affect the removal performance generally. Okay, so here is the lab experiment. Basically, I have the batch experiment. One is called river batch, another one is mineralization batch. So for the removal batch is the antibiotics I use is sulfonamide mixture of sulfamycin, sulfadiazine, sulfamethoxazole, and the 10 microgram gram per liter is a bit relatively higher than the concentration I found in the river, but it's also quite nature environmental related concentration. So it's just to compare to these 2 pathways, the And here is the removal performance of different sediment. So here are 2 panels I divided into riverbed sediment. So 3 different riverbed sediments and 3 different riverbank sediments. And this is the removal performance of these 3 antibiotics. And generally, the removal performance is better for riverbed sediment compared to riverbank sediment. But the exception is this one. So the sediment 1, riverbed from He field site, the removal performance is worse than the riverbank sediment from this field site. And I tried to find an explanation and look at the total organic carbon in this sediment. And I found for the sediment 1 is only 2.4, and for the sediment 2 is 4.2. So sediment 2 has a bit higher TOC, so maybe it explains, maybe it's just a guess, it will explain why they have a higher performance here. And also it makes sense when we compare the removal performance between the riverbank sediment. So we have decreasing in the TOC, so has a decrease in removal performance. But it's just need further further test to confirm this. And beside the removal performance, we also measured the degradation metabolites. So 3 often reported metabolites was included in the measurement. So aminomesosacol, this amino metabolites, and nitro metabolites. So this is different river sediment as shown in the last picture. And this is the concentration of the measured metabolites. And this is just some initial results, but we found no matter what kind of sediments and under aerobic condition, so the major metabolites is this amino sulfametoxazole. But this of course need to be further tested with the other samples that need to be analyzed in the lab. And besides the degradation base, I said I also use mutilation test because I haven't seen someone talking about mutilation test. So just briefly update a bit basic knowledge about the mutilation methodology. So as I introduced, carbon-14 labeled compound was used. And to do the measurement, first a base trap solution was prepared and an acidified solution. You put the base trap into the acid trap and take 1 milliliter sample of the batch test to put into the acid trap solution. So the mineralization product of CO2 will be released to the hot air and will be caught by the base trap solution. And then after incubate overnight, and it can be measured by the radioactivity. So the radioactivity will show the carbon-14 in the base trap and the carbon-14 in the acid solution. Basically, the radioactivity in the base trap samples, it shows the mutilation fraction of the carbon-14 labeled compound to CO2. It means how many CO2 was produced in this mutilation test. Actually, we see some difference, but I have to emphasize that this is only from 0 to 2%. So unfortunately, we feel like there's no mutilation for all of this sediment, for all of the carbon-14 compound. Yes. But likely we also find almost no mutilation, but still good removal performance compared to the degradation. So it must be not mutilation, not probably some other mechanism pathway happened here. And when we check the acid sample, we find the non-mutilation fraction of the carbon-14 labeled. It indeed like a difference between different sediments. And because this is a bit complex question to explain, so I will not take the time here. But if you feel curious about this, why it change, why the difference between different segments, you can just come and I would like to discuss why this is different. But anyway, it's just to show. Oh, sorry. It's just to show that the different sediment has no mineralization, but they do have different removal performance, both confirmed from the degradation batch and also from the mineralization batch. And as I said, I also want to evaluate the substrate effects on the mineralization. So for the mineralization stage, we have different treatment. So one treatment is I add extra carbon source, 5 grams per liter, and is similar concentration as we found in the river. and also 5 milligram nitrogen of ammonia nitrogen, and the other one is just no extra of carbon or nitrogen. And similarly, we find the different treatment shows no effect on the mineralization. But it's a bit difficult to say, but it has the effects on the non-mineralization part. They have some effect, but the effect is minor. But I do statistic analysis, they are significantly different. Okay, so just to summarize a bit, the substrate effects on the mineralization to CO2, not significantly, as shown here. But for the remove performance, it's minor, but significantly. Yeah, it needs to be tested further. So at the end, I would like to conclude. So in the study site, the North China Plain, the sediment almost have no mineralization, but a good remove performance generally. And the substrates have minor but significant effects on remove performance, because why I want to add this conclusion here, because I have some other tests to show is some difference, but it's not a big difference. And also the sediment composition, like the total organic carbon and all the microbial community, will affect the remove performance, because we have sample frozen in the -20, waiting for the analysis of the community. And the Riverbank filtration shows promising removal of the antibiotic micropollutants. So at the very end, I want to say thank you to this funding for this project, and also my research group at SUSTEC, and also my working partners at GILS Copenhagen, and also BWSTI at Beijing. And if you want to know more about the project, you can visit this link. Okay, thank you. Now I'm ready for questions. Hi.
I have a couple of questions. First of all, it's really nice to see the degradation when you have a constant input, but do you expect changes when you have a variable input? Because in reality, we expect the river will have a high antibiotic concentration, let's say in winter when people have the flu or whatever, and then do you expect that will have an impact on absorption, desorption, degradation?
You mean the initial concentration of the antibiotic? Of
the degradation rates, or the removal rates, let's say.
Yes, actually, I think it will affect for sure, because like a bit higher concentration also will show some inhibition effect, even though the inhibition effect cannot be evaluated yet. But the reason why we only try one concentration here is we want to compare parallel with the result from the batch and with the degradation. But I agree the concentration of the micropollutant will affect the degradation rate, and it should be emphasized.
And my second question was, you showed that sulfamethoxazole degrades, but we heard before that it degrades mostly in anaerobic conditions. Does it mean that the sediments that you were using were anaerobic or anoxic in the end?
Yes, actually in my degradation batch is all the time like oxic condition, because I measured the oxygen. But I also read a lot of paper that on the different redox condition, which one is more like which redox condition they have higher rate. But the publication are generally not like always the same. But we indeed detect a very good remove on the oxic condition. But I probably also on the anoxic condition, this sediment also have higher degradation rate. But we haven't tested it yet. That's going for the next step.
Thank you.